In this video, we will talk about what future value is. And I want to motivate this with an example. Alrighty, so in the example, it says that Dorothy's new job will pay her $80,000 per year, and her salary increases by $5,000 per year if she invests all of her income into some account and earns 4% interest annually, receives income and interest continuously. So that means that this income that she's getting from the job, she's receiving that continuously rather than like just getting it all at once or all every 2 weeks or whatever. And the same thing with the interest, she's earning that continuously. And she starts working on February 1st, 2020. How much will she make by April 1st, 2020? So 2 months afterwards, round to one decimal place. All right, so let's scroll it down a little bit. Alrighty, so let's start to break this down. Okay, so it's asking how much will she earn, how much will she make, how much will she have in her account by this date. So it's talking about how much she'll have at some point in the future, and we call this a future value. Alrighty, so what I'm going to begin by doing is writing down a function r of t for her income stream, for the money that she makes from her job. Okay, so it says that when she starts her job, she's earning $80,000 per year, but that increases by $5,000 per year. Okay, so I'm going to write a linear function for that because it's increasing in a linear way. It says every single year it's going to increase by 5,000. Okay, so it starts off at 80,000, and then every single year it increases by 5,000. So the 5,000 represents the slope, $5,000 per year. Okay, so that would be my function r of t. And what are the units? Dollars per year. This represents the rate at which she's receiving money from this job. So this is her continuous income stream. So the question told us to assume that her income she's receiving it continuously, receives income and interest continuously. All right, so what happens is as she's receiving income right away, she's depositing it and then earning interest on it. So the income she gets initially will earn interest for a longer time than income she gets later. Okay, so what I'm going to do is I'm going to draw a graph now. So I'm going to draw a graph. Let's draw some axes. And at this axis, I'm going to label with t. And t, because most of the units in the problem for time are per year. Right, those are these dollar amounts, 80,000 per year, 5,000 per year. Even the interest rate, it says annually. I'm going to say that this is in years. And with the other axis, I'm going to have that represent the amount in her account at time t. So in this situation, I'm going to assume that she has no money in her account initially. In fact, we know that. She's just starting this new job on February 1st. So initially, she shouldn't have any money in her account. Okay, so initially, she'll have nothing in the account. Whoops. And over time, that'll start to grow. And I'm not just drawing a straight line. I'm actually curving this upwards. Although it won't make that much of a difference in terms of my computation. Sorry, let me just draw this. Spread out a little bit longer. Okay, I'm going to draw a little bit curved because even though r of t is a linear function, she's going to earn interest. So over time, she'll earn even more and more because she's earning interest. Okay. So what I'm going to do now is we want to know what's happening from this starting time, February 1st. And I'm going to mark that here as just 0. That's my starting point. And then going to this ending point, I'll just put a tick mark there. But if I think about how many days have elapsed from February 1st to April 1st, well, you would have all the days of February, so that's 28 days of February, assuming it's not a leap year. So I'm going to assume that this is not a leap year. Not a leap year. In most questions, unless it specifically says that it is a leap year, the convention is we assume that it's not one. So 28 days in February, and then we'd have March on top of that, so 31 days in March. And that is 59 days. 59 days. Okay, but I'm measuring this axis in years, so I'd have to convert the days to years. And I'd have to divide by 365 to do that. So 59 over 365 years. We're going from t equals 0 to t equals this fractional value. And I'm going to use a Riemann sum. So I'm going to split this interval up into some subintervals. So I'll put some tick marks. And then within one of these subintervals, I'm going to draw a rectangle. And I'm going to draw the rectangle using a left endpoint. So I'm going to draw it like this. And the right endpoint, I'm going to call t sub I. The left endpoint, I'm going to call t sub I minus 1. Because it would be 1 before whatever ti is. Okay, so this horizontal distance between those two tick marks, we call this delta t. That's the width of this subinterval. So what I'm going to try to do now is, I'm going to try to figure out how much money she would earn from her income stream, from her job, over this time interval. And then add on to that how much she'd earn from interest, just from it sitting in the account. And if I could do that for every single one of these intervals and add them up, I can do my Riemann sum and let the number of rectangles go to infinity, and that would give me the total value in the account over this time period. Okay, so I got to begin that process by looking at just this subinterval. Okay, there we go. Okay, so I'm going to look at this subinterval. So the interval from t sub I minus 1 to t sub I. Okay, so on that subinterval, how much is she depositing? Well, we can approximate how much she's depositing by saying that the rate of change of her revenue initially on that subinterval, so at t sub I minus 1, if I plug that into this rate of change of her revenue, so that I would get r of t sub I minus 1. Okay, so that value, this is the rate at which she receives money. So I'm going to estimate that on this time interval, that the rate at which she receives money is just constant. That's why this is going to be an approximation. And if it's constant, what I would have to multiply this by to get the amount of money she earns over that interval. Sorry, not how much she earns, but how much is deposited, is I'd have to multiply this by how much time passes. How much time has elapsed. And the elapsed time, we're calling that delta t in the picture. Okay, so we're multiplying those. And that will tell us how much is deposited in this time interval. In this time interval. Okay, but we also have to factor in the fact that she's going to earn interest. Okay, so she'll get this quantity that she deposits, but then that quantity that she deposits is going to earn interest for a certain amount of time. How much time is this going to earn interest for? Well, we've marked sort of the starting point as t sub I minus 1, and we care about measuring what's going on starting at that time until the end of this interval, up to 59 over 365. So this orange little bracket here, this is the time to earn interest on this deposit. So this is how much time the money that's deposited in this time interval will have to earn interest. If I were to look at a different time interval, it would have a different amount of time to earn interest. It just depends on how much time is left until the end of the interval. Okay, so if I measure how long this is, I got to do the bigger value minus the smaller one. So that would give me 59 over 365 minus the smaller one is t sub I minus 1. So this the money that's deposited in this time interval is earning interest for this amount of years. So now if I know how much was deposited during that time interval and how long it's earning interest for, because I know it's earning interest compounded continuously, I can use my formula P times e to the RT, so that PERT formula for continuously compounded interest, to determine, well, how much is that going to be worth at the end of this time period? Okay, so P is sort of, it represents the initial amount, which in this case is how much was deposited at this time interval, which is R of ti minus 1 times delta t, and then we multiply that by e to the RT. Okay, and this is going to represent the amount I'm actually going to say this is the amount this deposit. So by this deposit, I mean how much was deposited during this time interval, this sub-interval. This deposit is worth at the end of the entire time period. So in this case, it's when we reach that 59 over 365 years marker. So that was at the end of these 2 months. Okay, so now on the right-hand side, I'm going to write down, well, what is R of ti minus 1 and everything? So I'm going to plug t sub I minus 1 into my function for R of t, and that'll give me 80,000 plus 5,000 t sub I minus 1 times e to the R and then for this t in the e to the RT, I have to put how much time that this deposit was earning interest for. So I was doing it for 59 over 365 minus t sub I minus 1 years. And then finally we have that delta t at the end. Okay. So I'm moving this to the next page to give myself some more room. So this quantity right here, this represents how much, it represents what the value of the quantity that was deposited during that small time interval is going to be by the end. Okay, so I have to do that for every single interval and add them all up. So that's where I'm going to do a sigma. I'm going to do a sigma from 1 to n. And that's going to mean I'm doing this for n subintervals. But to make this exact, I need to take a limit. I got to take the limit as n goes to infinity. And when we do that, this will tell us the value of this income stream on top of that interest by the end. And we call that the future value. The future value, or sometimes we just call that FV to abbreviate it. Okay, but we've seen these limits of Riemann sums before. We can rewrite these limits of Riemann sums as definite integrals. So this is going to be a definite integral. So I'll have an integral. What's my time period here? Well, it starts at t equals 0, and it goes to 59 over 365 years. And then I write down my function that showed up in sigma notation. I just change the t sub I minus 1s to t's. So we get 80,000 plus 5,000 t times e to the 0.04 times 59 over 365 minus t. And then the delta t changes to a dt in the definite integral. Okay, so we convert that to a definite integral. That's really nice. So this is something that we could work out. At this point, what I'd like you to do is, I don't want you to fully work it out, but I want you to pause the video for just 1 minute to see if you can identify, well, what is the technique that I need to integrate something like this? 4, 3, 2, 1, pause that video. Pause it for just a minute to think about what technique could we use to integrate this. All right, hopefully you did that. Hopefully you paused it for about a minute to think about that. So this is great for integration by parts. This is good for integration by parts because if I let this 80,000 plus 5,000t, if I let this be u, it has a really simple derivative. The derivative is just a constant, 5,000. And that'll make the integral that I get from doing integration by parts be easier than this one. Okay, so I'm going to skip that. I'm going to skip the integration by parts because mostly I cared about like the setup, the concept behind this and how we set it up. If we work out what this is, we end up getting 13,000, and 38.9. I said around to 1 decimal place, and we get this when we do. So that is how much she would earn over this 2-month period from her job salary, on top of the fact that she's earning interest over time. Okay, so in general, if income is received over a time period from t equals a to t equals b at a rate of r of t dollars per unit of time, so r of t is going to be some function that represents the rate at which income is received, and right away that income is deposited at an interest rate of r per unit of time, compounded continuously, then the amount in the account at a future time, t equals b, we call that the future value, or FV. And the general formula for this is we get an integral from a to b, the starting time to the ending time. In my example above, that was 0, that was the starting time, to 59 over 365. That was the ending time, 59 days in the future. And we are integrating our function for the income stream, which was r of t, times e to the something. It's e to the r times t minus b, where b is that ending time, dt. I'm getting this, whoops, looks like I got that backwards. I think this should be b minus t, yep. So r times b minus t. And if we zoom it out and we compare this to the integral that we had above, it has the same general form. R of t, I had that written here in the front. And then I had e to the r times b, the ending time, minus t. Okay, so that is our key formula from this section. This integral formula in general is how we would compute future value. So for future problems that we work out involving future value, we can go straight to this integral formula. We don't have to do the Riemann sum every single time. I wanted to do that in this video to really demonstrate where does the integral formula come from. So in terms of our goals for this section, we've talked about how to compute future value and what it is. In the next video, we'll talk about what present value is and how to compute that.